this time I'd like to go ahead and try to talk you through Gauss's law for spherical geometry. Okay, and I'm going to try to do a video with a whole lot of different cases of spherical geometry and how to find the electric field strength at different points for different distributions of charge. So here we go. So we're going to do case one. Okay, case one is just, it's something that we could do without Gauss's law, something we could do with just Coulomb's law, and that is for a point charge. So what we're going to do is we're going to say, find E at a distance R away from a point charge. Q. Okay, so I'm telling you two values there. The picture, you say, well, of course, the picture is going to look like this. We've got this point charge, this Q, little point charge there, this Q. And we want to find the E field strength, some distance, little r away from that point charge. So right there, say, how strong is the electric field strength there? So my first step is to go ahead and draw in the electric field. Which you say, that's okay. I know the electric field from a positive charge will radiate outward. And we're going to use that to design our Gaussian surface. So you remember Gauss's law says that our flux is the surface integral of electric field strength dot dA. And that's equal to the charge inside over epsilon naught. And so this requires us to design a surface integral over a closed surface here. But we want to choose any surface that surrounds this charge would work. But we want to find electric field strength here. So we want to calculate the E field there specifically. So our area has to pass through that point. Secondly, it's got to be a closed surface. It needs to have charge inside it, or else we're going to get a net flux of 0. So I need to surround this charge. Lastly, because it's a dot product, we're going to have to worry about the cosine of the angle between the electric field vector and the area vector. So the shape that's going to make this integral easy to take is going to be a sphere. Okay, a sphere that's centered on the charge and that passes through this point. In other words, a sphere of radius little r. And so we'll draw our Gaussian surface around like that, make our little bubble. And we know that the area vector always points normal to the surface and outward. So my little area vector, basically what we're going to do is we're going to end up splitting that surface area into a bunch of little d areas. Each little d area, little bit of area, for this little bit, and this little bit, and this little bit, and this little bit of the surface, they all point straight outward, all my little dAs. And if I do, at every point, the E field dot dA, for this particular surface, that angle, they're always going the same direction. And so the cosine theta from the dot product is really going to be, in this case, a cosine of 90. So when I do this calculation, several important things happen. That angle is going to be consistent everywhere around, so it's a constant, so that cosine theta can be factored out of the integral. Secondly, the electric field strength has to do with the separation of those field lines, right? How closely packed they are. But just kind of logically, by symmetry, the field spreading out in space from a point in 3 directions, anywhere on the surface of a sphere, that same distance out, will be, that by symmetry, it's going to be the same separation of the field lines everywhere, right? The field's going to be the same strength at a distance r away from this charge in any direction. And so that E is a constant value at anywhere on the surface of that sphere, so that E field strength will move out of the integral too, because it's a constant. I can factor it out. So I have E cosine of, in this case, 0 degrees, and then all that's left is that surface integral dA. You say, well, this just says add up all the little bits of area, all little dAs, all little bits. I'm taking the surface, I'm just chopping a bunch of little tiny little pieces. Well, that will just add up to be the total surface area of that sphere. And the surface area of a sphere is 4 pi r squared. That's the geometry formula. Conveniently found on the backside of your AP Physics formula sheet. Cosine 0 is 1. Now the right side. Right side says we want all the charge that's inside our Gaussian surface. Well, in this case, the only charge in is Q. So that's just big Q. And that constant epsilon naught. Just tracking that down. Move this 4 pi r squared over. We'll have E is 1 over 4 pi epsilon naught times Q over r squared. And we might recognize this as the E field for a point charge from Coulomb's law. And so we get the same answer out. This 1 over 4 pi epsilon naught, that's just the Coulomb's law K, if you like saying it that way. Same thing. Okay. These two statements are equivalent. Okay. Same. There are many AP Physics teachers are very picky, and they say, hey, I want everything to be in terms of the true universal constant, in terms of epsilon naught. And in fact, I believe on the AP formula sheet, they don't write it this way. They write it this way on the actual formula sheet. On the table of constants, they do have the Coulomb's law K and say, hey, that's equal to 1 over 4 pi epsilon naught. And so it's okay. I mean, the physics, the graders of the AP Physics exam will accept either way. But it's probably safest to always write it the way they're expecting. And I think they're expecting it with the epsilon naught. And that's the way it looks in the base formula. It's always a good idea to start with the base formulas. So that's it. All right. So that's the point charge. Now let's do another what if. What if we went ahead, so this is going to be case 2. I want to find E at a distance r from the center of a sphere of uniformly distributed charge. Q. That has a radius r. Okay. Where r is greater than r. Okay. So, in other words, what I'm doing now is a similar setup, except this time, instead of being a point charge, that charge Q is spread out into a sphere of radius big R. So that looks like this. There's my sphere, and my charge is spread out throughout that sphere. This charge Q. And this guy has a radius big R. Okay, and we want to find the electric field strength way out here somewhere. Okay, where this whole length here is little r, and I want to know right there what's my electric field strength. Okay, so at little r, greater than big R. And so if I do that, then again, I would draw my electric field, which is going to radiate outward. Okay, that's my E field lines. And again, I have to design a Gaussian surface, right? A surface to count the flux through, count all the flux punching through. And it makes sense, again, I want to make my surface so that it's going to be a uniform E field strength everywhere on the surface. And the surface has to pass through the point where I'm trying to find the electric field. And so, again, I'm going to do a sphere, okay, with a radius little r, okay? So the setup here, the winning setup here to apply Gauss's law is identical to the setup here. And in fact, when I do the calculation, this whole it'll all look the same, right? It's still going to be my little area vector at every point on the surface goes outward. My little area vectors, my little dAs. And so they're going to be parallel to electric field vectors. And so again, it's going to be a cosine of 0 degrees. The E is going to be the same everywhere by symmetry. It's the same spacing on the field line, same strength field everywhere. So the E is going to can be factored out of the integral. The cosine theta is going to be 0 degrees everywhere, factored out of the integral. The surface area is all that will be left. The surface area of the sphere is a sphere of radius little r. That'll be 4 pi r squared. And on the right side, the charge inside, well, the total charge in is still Q, it's still big Q. And so that's just going to be big Q, be able to charge inside. I'm going to get the exact same answer out. That was easy. Now the tricky one. So now I'm going to have to slide this over. You say the next case is going to be, hey, same setup, but now what if, I want to find the electric field strength for this, but what if R was less than R? In other words, what if R is inside that sphere of charge? That's going to be a little trickier. So I'm going to call this case 3. Now, I'm just going to squeeze it in here on this board so that I don't run off out of your field of view here. We're going to say case 3. I'm just going to squeeze it in. Same, but for R less than big R. Okay, little r less than big R. Okay, in other words, inside the sphere of charge. Okay, I'm going to draw right on the same diagram if you don't mind. So right here, let's say we want to find right there, hey, at a little distance, little r here, hey, what's the E field strength there? And you say, well, I'll need to do a Gaussian surface. We'll have to pass through that point because that's the point where I want to find the field strength. And again, I want to make the E field the same strength everywhere there. So I'm going to be dealing with this spherical symmetry. My boundary, my Gaussian surface, is going to pass through around like this, right? And once again, if I do the calculation here, you say again, the E field will be constant everywhere on this bubble. The cosine will be 0 because the area vector for that bubble always points outward, normal to the surface and outward, my little dAs, right? So that's all good. They're going parallel to the E field, and so that'll be cosine of 0 again. It'll be everywhere on the surface like that, so it pops out of the integral, it's a constant. And the integral will just be 4 pi little r squared. The left side looks identical. But the right side is going to be different because I just want the charge that's inside my bubble and inside my Gaussian surface, and I don't have the whole sphere inside the bubble. What I want is just the charge that's in here. I just want this charge right in here. I don't want this outer part. It's interesting that this charge that's out here doesn't matter for this calculation. In this outer part, with the shape, it's like a hollow sphere, right? It's a spherical shell. And you say, the stuff in that shell, the stuff that's exterior to the point I'm interested in, doesn't matter. Why not? Imagine one little bit of charge out here. One little bit of charge that's outside. If I drew the field for that guy, the field lines that guy makes would radiate outward. Any field that went into this bubble would pass out the other side. And since flux in is negative and flux out is positive, they would just cancel out. Any field lines would cancel out. They would contribute nothing to the flux. No net flux from charges outside. And so we don't need to worry about them. I just care about the charge that's interior, inside my Gaussian surface. Neat. Well, it turns out that because the charge is uniformly distributed, what that means is, if this volume here was half the volume of the whole sphere, the volume in my bubble, my Gaussian surface was half that, it would have half the charge. If this was a fourth of the total volume of this sphere of charge, it would contain a fourth of the charge. If it was a little d volume of the whole, it would be a little dq, infinitesimally small bit. The point is, there's a set ratio, right? That charge to volume is a set ratio. Half the volume, half the charge. So what that means is, I can set up the ratio and do a trick to find out how much of the charge is in. So I set up a ratio. Because it's uniformly distributed, I can do this. And so what I'll do is I'll just say, look, for this calculation, we'll say the ratio of the charge in to the total charge is equal to the ratio of the volume in the Gaussian surface to the total volume of this sphere of charge. I'll move this Q to the other side. And I have volume in over total volume, right? Now volume in, the formula for the volume of a sphere. And again, if you forget this, guess where it is? Yeah, there's a bunch of math formulas on the backside of the AP formula sheet. But you're going to memorize this. 4/3 pi r cubed. This is the volume that's inside this bubble. Remember, this is a bubble of radius little r. Little r. Over the total volume of the charge. All the charge. Well, all the charge is in a sphere of radius big R, right? That's what this is. So this will be 4/3 pi big R cubed. Okay, so that's it. So that ratio, that's, right, times q, that's the amount of charge that's inside it. So I can see that 4/3 pi will cancel, 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 cancel. And so the q that's inside my bubble will be big Q, little r cubed over big R cubed. So this is what's going to go in here for Qing in the calculation. And so, if I do that, and am I really going to squeeze into this bottom part here? Yeah, I am. You know me, I'm going to do that, right? I need to squeeze this in here, do this calculation. So, copy, 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 copy this left side. I'm just going to copy all the way down. So when I do that Gauss's law, the left side I'm going to get E times 1 times 4 pi little r squared. On the right side, Q in over epsilon naught. Q inside the bubble over epsilon naught. And for Qn, we're going to use this. So this will end up being E times 4 pi r squared, little r squared. On the right side, I'm going to have Q, big Q, little r cubed over big R cubed. And I've got this epsilon naught. Don't forget that little epsilon naught there. Left behind from the formula, from Gauss's law. Okay, hey, we can move this over here. And when I do that, instead of going below, because I'm running out of space, I'm going to go sideways. Sorry. That's right. This is where it all went sideways. You're going to end up with, see this 4 pi is going to go to the number, 4 pi epsilon naught. You're like, oh my gosh, that's that Coulomb's law K if I want it. R squared is going to cancel 2 of the r's here, right? R squared just cancels out that, right? You know what I mean? And so what I'm going to end up with is just 1 r on top. I'm going to have Q over r cubed. I'm just going to have 1 r left. So this, oh, bad shooting. This is what I'm getting. All right, fine. I'm just going to read it, copy that. So I get, if you want, kq over big R cubed times r. Now, notice that everything I put in parentheses here are all constants in this calculation, right? There's a constant total charge here. It has a set big radius, big of all the charge. Obviously, universal constant. You say, so my variable, as I go further out, you can see that the E field strength is directly proportional to the radius while I'm inside the sphere. Once I get outside the sphere, though, as I head out, I'm not adding any more charge. I just have this charge that's inside here, right? When I'm inside, you say I've got now the full charge. As I keep going out, now it's just going to act like a point charge. If I'm outside of the sphere, I can treat it like it's a point charge. Anytime I have radial symmetry, if I'm outside the sphere, this nice symmetric sphere of charge, I can treat it like all that charge was focused to the point. That is a really super useful idea. But if I'm inside, if it's uniformly distributed, it's proportional to R. So last thing, and I didn't leave myself much space here, so I'm just going to go ahead and erase and pretend that wasn't there. I'm going to say, last thing, if I made a graph of electric field strength versus distance from the center of the sphere, for the sphere of uniformly distributed charge. So here's, right here, this is little r equals 0. And right here, that's little r equals big R. While I'm in here, my E is directly proportional to R. When I'm out here, it acts like a point charge. My E is proportional to 1 over r squared. And if I did my graph field strength would look like this then. Linear, and then 1 over r squared curve. Okay. Now, is my charge in spherical geometry always going to be uniformly distributed? Nope. There will be times where it's not distributed evenly through here. In fact, it kind of makes sense if you can imagine I had a fluid and I had like some ionic compound dissolved in it maybe. Then if somehow I was able to draw off a bunch of spare electrons, then you say, hey, this positive ions, they don't want to be near each other. They would tend to flow to the surface maybe. Those positive charges would repel each other. It might make sense for the charge to not be uniformly distributed, but to become more densely packed as I head to the surface. That would be a different problem, and I would not get this nice linear function inside, right? Now, if I was outside, it's radially symmetric. Even if it gets more densely packed, the charge ahead of the surface, if I'm outside, I can still treat it like a point charge in the middle, right? It'd still be kq over r squared when I'm outside. When I'm inside, that's trickier. I think I'm going to put that in another video. So let me go ahead and stop this one here. So we looked at the first 3 cases for spherical geometry: a point charge uniformly distributed in a sphere when you're outside, and when you're inside the sphere. All right. See you next video.